What specific problem does your proposed method, particularly the MASSIVEDS Datastore, aim to address in the context of retrieval-based language models?
The proposed method, particularly the MASSIVEDS Datastore, aims to address the limitations of existing retrieval-based language models, LMs, that typically utilize smaller, single-domain data stores, such as Wikipedia, which contain only a few billion tokens. This approach has been shown to restrict the performance and generalizability of retrieval-based LMs across diverse tasks. In contrast, MASSIVEDS is a massively multi-domain data store comprising 1.4 trillion tokens, integrating both general web data and domain-specific data from various high-quality sources, including books, scientific papers, and community Q&A platforms. One of the key challenges in studying datastore scaling is the computational cost associated with constructing and evaluating data stores of varying sizes and compositions. To mitigate this, we developed an efficient datastore construction pipeline that reduces the compute requirements by over an order of magnitude, making it feasible to conduct extensive scaling studies on a modest computational budget. This pipeline allows for systematic evaluation of the effects of scaling massiveds on retrieval-based LMs, revealing that datastore scaling consistently improves language modeling and downstream task performance in a task-dependent manner. Furthermore, our findings indicate that retrieval-based LMs can outperform larger LM-only counterparts when leveraging the MASSIVEDS datastore, particularly on knowledge-intensive tasks. This suggests that the ability to retrieve relevant documents from a broad data store enhances the model's factual recall and overall performance. By opening up massiveds for public use, we aim to spur further research into the benefits of large-scale data stores, ultimately addressing the need for improved factuality, domain adaptation, and parametric efficiency in retrieval-based LMs. Overall, massived serves as a critical advancement in the field, enabling better compute-optimal scaling trends and enhancing the performance of retrieval-based language models across a wide array of tasks.
Can you explain in detail how the MASSIVEDS pipeline operates? Please illustrate the main steps involved in constructing and evaluating the datastore, including any novel components introduced in your methodology.
The MASSIVEDS pipeline is designed to efficiently construct and evaluate a large-scale datastore for retrieval-based language models, LMs. The main steps involved in this pipeline include data filtering, data subsampling, indexing, document retrieval, and evaluation, with a focus on minimizing computational costs. 1. Data filtering. The first step involves cleaning the raw text corpus through deduplication, decontamination, and quality filtering. This ensures that the data used in the datastore is of high quality and relevant for the tasks at hand. 2. Data subsampling. After filtering, the pipeline randomly subsamples a fraction of the text corpus to achieve the desired datastore size. This step is crucial for managing the scale of the datastore while retaining diversity in the data. 3. Indexing. A significant innovation in the MASSIVEDS pipeline is the reordering of operations to optimize computational efficiency. Indexing is performed early in the process, where the filtered data is embedded using an auxiliary model, creating a searchable index. This step is computationally expensive, so it is executed only once and shared across all subsequent datastore variants. 4. Document retrieval. Following indexing, the pipeline retrieves a relatively large number of documents, 14 for each query. This allows for a more comprehensive selection of documents to work with, which can then be filtered in later steps. 5. Evaluation. The final step involves evaluating the performance of the retrieval-based LMs using the top retrieved documents. For evaluation, the top 5 documents are used to augment the input to the LM, which is then assessed on various tasks, including language modeling and downstream tasks. The MASSIVEDS pipeline significantly reduces computational requirements by an order of magnitude compared to a naive approach, which would involve repeating expensive operations for each datastore variant. This efficiency enables the study of datastore scaling on a modest compute budget, making it accessible for broader research. Additionally, the pipeline's design allows for flexibility in experimenting with different datastore sizes and compositions without incurring prohibitive costs. The results obtained from the MASSIVEDS pipeline are shown to be equivalent to those from a naive pipeline with high probability, ensuring reliability in the findings. Overall, the MASSIVEDS pipeline represents a novel approach to constructing and evaluating large-scale data stores, facilitating advancements in retrieval-based language modeling.
What advantages does the MASSIVEDS approach offer compared to existing single-domain data stores, particularly regarding performance on language modeling and downstream tasks?
The MASSIVEDS approach offers several significant advantages over existing single-domain data stores, particularly in terms of performance on language modeling and various downstream tasks. Firstly, MassiVEDS encompasses a diverse composition of data, including both general web data and domain-specific data, which allows it to outperform single-domain data stores in language modeling tasks. For instance, the paper highlights that MASSIVEDS significantly outperforms in-domain data stores on language modeling, trivia QA, and MMLU, while matching performance on natural questions, NQ, and MED-QA. This indicates that the broad data coverage of MASSIVEDS enhances its ability to generalize across different tasks. Secondly, the retrieval-based language models, RIC-LMs, utilizing MASSIVEDS demonstrate superior performance on knowledge-intensive question-answering tasks, such as NQ and TQA, where retrieval-based LMs consistently outperform LM-only baselines across all scales. The findings show that a smaller model, like Llama 2.7b, can outperform larger LM-only counterparts when retrieving from MASSIVEDS, underscoring the effectiveness of storing knowledge in a comprehensive data store. Moreover, the paper notes that the retriever in MASSIVEDS tends to retrieve relevant documents even in the presence of out-of-domain data, which enhances robustness and performance. This contrasts with single-domain data stores, which may struggle to provide relevant information when the query does not align perfectly with the data source. Additionally, the MASSIVEDS approach allows for better compute-optimal scaling trends, as it achieves superior performance compared to LM-only models at the same training cost. This is particularly advantageous because it enables researchers to leverage large-scale data without incurring the high costs associated with training larger models. In summary, the advantages of MASSIVEDS over single-domain data stores include improved performance across a range of tasks due to its diverse data composition, the ability to outperform larger models with smaller retrieval-based models, enhanced robustness in document retrieval, and more efficient compute scaling, making it a valuable resource for advancing retrieval-based language modeling.
How did you validate the effectiveness of the MASSIVEDS data store and the proposed scaling method? What experimental setup did you use, and which metrics were employed to assess performance?
To validate the effectiveness of the MASSIVEDS data store and the proposed scaling method, we employed a systematic experimental setup that involved constructing and evaluating various data stores of different sizes and compositions. The MASSIVEDS data store, comprising 4 trillion tokens from both general web data and domain-specific sources, served as the foundation for our scaling study. We designed an efficient data store construction pipeline that significantly reduced computational costs, allowing us to explore the effects of scaling on retrieval-based language models, LMs, with varying parameters and pre-training tokens. Our experimental setup included evaluating both language modeling and downstream tasks. For language modeling, we measured perplexity on datasets from 2 domains: general web data sampled from REDPAJAMA and scientific paper data from S2ORC. We also assessed performance on diverse downstream tasks, including general knowledge question answering QA, with datasets like trivia QA TQA and natural questions NQ, as well as reasoning tasks such as the Massive Multitask Language Understanding (MMLU) and MED-QA. The metrics employed to assess performance included perplexity for language modeling, which indicated how well the model predicts a sample, and accuracy or performance scores on downstream tasks, which reflected the model's ability to retrieve and utilize relevant information effectively. We found that Datastore scaling consistently improved language modeling performance as evidenced by lower perplexity scores, and enhanced performance on knowledge-intensive tasks where retrieval-based LMs outperformed LM-only baselines across various scales. Additionally, we conducted ablation studies to analyze the impact of different retrievers and evaluated the performance of retrieval-based LMs against LM-only models under the same compute budget. This comprehensive evaluation demonstrated that retrieval-based LMs could achieve superior performance by leveraging the MASSIVEDS Datastore, validating the effectiveness of both the Datastore and the scaling method. Overall, our results indicated that increasing the scale of data available at inference time significantly enhances model performance across multiple tasks.
What were the key findings from your experiments regarding the performance of retrieval-based language models using MassiveEDS on knowledge-intensive tasks? Can you provide specific metrics or examples that highlight these results?
The key findings from our experiments regarding the performance of retrieval-based language models, LMs, using MassiveEDS on knowledge-intensive tasks are significant and multifaceted. First, we observed that Datastore scaling consistently improves performance on knowledge-intensive question-answering tasks, such as natural questions, NQ, and trivia QA, TQA. For instance, a Llama 2 7B model retrieving from fewer than 100 billion tokens outperformed both its 13B LM-only counterpart and the larger Llama 3 8B model on TQA and NQ, demonstrating the effectiveness of leveraging a large datastore for factual recall. Specifically, our results indicated that retrieval-based LMs significantly outperformed LM-only baselines across all scales, with performance monotonically increasing as the datastore size grew. This trend was particularly evident in knowledge-intensive tasks, where the retrieval-based approach allowed smaller models to achieve superior results compared to larger LM-only models. For example, the Llama 2 7B model, when retrieving from MASSIVEDS at its largest scale, showed a marked reduction in perplexity, indicating improved language modeling capabilities. Moreover, we found that Datastore scaling had a pronounced impact on the performance of models on the Massive Multitask Language Understanding (MMLU) benchmark, where performance improved across all model scales. However, the results were more mixed for MED-QA, where only the weaker Llama 2 7B benefited from Datastore scaling, suggesting that the complexity of the task and the quality of the data in MASSIVEDS may have influenced these outcomes. In summary, our findings highlight that retrieval-based LMs can leverage large, diverse datastores like MassiveEDS to enhance performance on knowledge-intensive tasks, achieving better results at lower training costs compared to traditional LM-only approaches. This underscores the importance of datastore size and composition in optimizing model performance for specific tasks.
What limitations did you encounter with the MASSIVEDS method, especially concerning the types of tasks it performed well on versus those it struggled with? How do you see these limitations influencing future research in this area?
The MASSIVEDS method encountered several limitations, particularly in its performance on reasoning-heavy tasks compared to knowledge-intensive tasks. While MASSIVEDS demonstrated significant improvements in knowledge-intensive question-answering tasks like trivia QA and natural questions, NQ, it struggled with more complex reasoning tasks such as Massive Multitask Language Understanding (MMLU) and MED-QA. The findings indicated that retrieval-based LMs, particularly the weaker Llama 2 7B model, benefited more from datastore scaling in knowledge-intensive tasks, outperforming larger LM-only models. However, for reasoning-heavy tasks, the performance of smaller models did not surpass that of larger models, suggesting that the complexity of these tasks requires more advanced models and potentially more specialized data sources. Additionally, the study highlighted that MASSIVEDS might lack high-quality data necessary for effectively addressing reasoning-heavy tasks. The limited inclusion of relevant data, such as textbooks for MMLU and biomedical literature for MedQA, could hinder the model's ability to retrieve pertinent information, thereby affecting performance. This limitation emphasizes the need for future research to explore better data sources and improve the quality of the data store to enhance performance on reasoning-intensive tasks. Moreover, the research pointed out that while the MASSIVEDS pipeline allows for efficient scaling studies, it is still constrained by available computational resources. This limitation restricts the ability to experiment with various retrievers and their impact on data store scaling trends. Future research could focus on developing more efficient retrieval methods and re-rankers to improve performance across a broader range of tasks, particularly those requiring complex reasoning. Overall, addressing these limitations will be crucial for advancing the capabilities of retrieval-based language models and expanding their applicability to diverse tasks.